So in this video we'll look at ionizing or dissociating strong electrolytes. How we actually do that, which ones do that, and in particular, how can you tell? So in this video cast we want to answer the question, how do we know if something is strong? If you remember from our past video cast, we made a table that looked like this with a categorization of strong things, weak, and non. These, of course, are the most special because those are the ones that conduct electricity. And we want to know, how do we recognize these when we see their chemical formula or their name? And then how do we illustrate them with their positive and negative charges? So, the categories in the strong electrolytes are first the strong acids, and there are 7 of them. And you can memorize them pretty simply by doing the strong acid Ch4, which is Hyber, Hickel, High, Hono, Hickalo, H2SO4. So once again it goes Hyber, Hickel, High, Hono, Hickalo, H2SO4. Say it along with me this time. Hyber, Hickel, High, Hono, Hickalo, H2SO4. One more time for practice. Hyber, Hickel, High, Hono, Hickalo, H2SO4. You now know the 7 strong acids, as long as you know that Hickalo is not HClO 3/4, but HClO3 and HClO4. The strong bases are also easy to remember. Oh, by the way, if it's not one of these acids, but it starts with an H, it's a weak acid. And so lots of times people come back and say, how do you know if something's a weak acid or not? Well, it's not one of these. If it's not one of these, that's why I say it's most acids in the world, because most acids are weak. These are the only strong ones. The strong bases are also easy to remember if you have a periodic table nearby. Remember that the strong bases are the hydroxides of the group 1 and some group 2 metals. So group 1 and group 2 are these lithium, sodium, potassium, rubidium, and cesium hydroxides, and then calcium, strontium, and barium, and they form the B on the periodic table. So if you're ever asked which ones are the strong bases, just pull out your periodic table and look at them. Just remember that these are going to have 2 OHs next to them. Perhaps the most confusing for students is, how do we know this group called the soluble ionic compounds? The strong acids are no problem. Hyber, Hickel, High, Hono, Hickalo, H2SO4. The strong base is not a problem. They form a B on the periodic table. But how do I know which ionic compounds dissolve in water? First of all, what is an ionic compound? Well, an ionic compound is also known as a salt, and it's something that contains a metal and a nonmetal, or 2 polyatomic ions. So they were the ones that you named last chapter, and they contain a metal, one of these guys over here, and a nonmetal, or they've got some of these polyatomic ions in them with a metal or 2 polyatomic ions stuck together. So how do we know which ones are soluble? Well, there's a table inside your periodic table, right here, this table. This is called the solubility rules table. And I'll give you a way to remember it a lot, but you'll always have this available to you, but you want to become really familiar with it. So let's zoom in on it. If you don't have this out, pause the video now and take it out, because we'll put a few notes next to it. Okay, so anything that contains a nitrate, like for example potassium nitrate or copper nitrate, anything that contains an NO3 is always soluble, and therefore it's a strong electrolyte because it's an ionic compound that is soluble or dissolves. Anything that contains an acetate, for example NaC2H3O2 or NiC2H3O2. Notice they wrote acetate both ways, the Ch4 way right here and the C2H3O2 way. Anything that contains a chlorate is soluble. So something like LiClO3 or Fe(ClO3)3. These would be soluble ionic compounds that are strong electrolytes. These three can always be soluble. Can meaning chlorate, acetate, nitrate. Oh, you can remember those three are always soluble. The next three are close by on the periodic table. These are the three halogens, chloride, bromide, and iodide. And these are always soluble, except there's a pattern to three things that are not. Silver, mercury, and lead. Silver, mercury, and lead happen to not be soluble with chlorides, bromides, and iodides. Otherwise, they're always soluble. HAP stands for Hg for mercury, Ag for silver, and Pb for lead. So you can happen to remember that all chlorides, bromides, and iodide containing substances are soluble unless it contains HAP. Sulfates are also always soluble except for 5 different things. And these 5 different things spell a nice word, PHABS, FABs. So they're always soluble except for FABs. FABs would be Pb for lead, Hg for mercury, Ag for silver, Ba for barium, and S for strontium. Now calcium is also listed in here, and you can remember it because calcium, strontium, and barium are right next to each other in the same group. And believe it or not, there are different solubility rules tables in the world that don't include calcium. And you'll also see that there are stars next to some of these, and then if you look at the bottom and what the star means, it means that these are slightly soluble. And so these are approximate rules, and you have to be okay with that right now until you get to chapter 17 and you can put some math to this. But until then, you can just know that these are pretty much either always soluble or these happen to pretty much not be soluble. 2 other things are mainly water soluble. These are all the cations from group 1 and ammonia. So the cations from group 1 are lithium, sodium, potassium, rubidium, cesium. So you have to write those in here. Lithium, sodium, potassium, rubidium, and cesium. And then the polyatomic ion, ammonia. And so if it contains any one of these ions, it's always soluble. So if you look back up here in my potassium nitrate, it turns out to be AA soluble because nitrate's always soluble and potassium soluble. Oh, here's my lithium, same thing. And here's my sodium. Sodium also makes this soluble. It's AA soluble because it's got those. Or if I had something like ammonium carbonate, well, this would be soluble because it contains ammonia in it. Oh yeah, NaH4. Now this is probably the most confusing piece right down here on the mainly water soluble. It says H+, all common inorganic acids and low molecular mass organic acids are soluble. This is true. They're soluble. And if you look back at your chart, you can see that acids and bases are listed right here, and you'd say like, oh yeah, those dissolve, and they completely dissociate. They're the strong acids. But then you'd go over here and you'd say, wait a minute, aren't most acids over here? It means that they are soluble, yes, they dissolve in water, but they're only weak electrolytes, meaning that they only sort of break up into positive and negative ions. Only a little bit, and so they only conduct a little bit. And so keep those words separate in your mind. Keep those words separate in your mind. Soluble versus strong electrolyte. This means it forms lots of positives and negatives when it's dissolved. Soluble just means it dissolves in water and is aqueous. And so you could think of it kind of like as a little circle diagram where you'd say strong electrolytes are this group of species, but to be a strong electrolyte, you have to be soluble. Now, inside the soluble things would also be weak electrolytes, but those would be separate from one another. Both would be soluble inside of this bubble of solubility. The strong electrolytes would be the ones that give you lots of pluses and minuses. The weak electrolytes wouldn't give you very much pluses and minuses. And even lots of non-electrolytes, they would dissolve and be soluble. Non-electrolytes, they'd be included in the solubility bubble, but they wouldn't give you many positives and negatives. So in summary, here are the things we wrote down. Chlorates, acetates, and nitrates can always be soluble. These are on your periodic table right here. Chlorates, acetates, and nitrates. Chlorides, bromides, and iodides are always soluble except for HAP, mercury, silver, and lead. Sulfates are always soluble except for FABs, lead, mercury, silver, barium, and strontium. And then you can remember calcium just because it's on the periodic table close to it. And then group 1 and ammonias, they're always soluble. Now there's a bunch of rules down below here for mainly water insoluble things, and they're nice to look at. But what you need to know is if it's not on here, then it's insoluble. If it's not on here, it's insoluble. It's probably listed down here, but there are things that aren't listed down here that are also insoluble. So how do we illustrate these things? How do we illustrate these things that are strong, weak, or non-electrolytes? The ones we're mostly focused on are the strongs, because these dissociate or break up into ions. The weak and the non don't. So let's go through and classify them, and if they're strong, let's dissociate them. Example problem number 1, calcium chloride. Well, first of all, we've got to look at our list right here and decide, is this a strong, a weak, or a non-electrolyte? Well, it's got a metal. How did I know that? Because it's on the periodic table right here, and it's got a non-metal, chloride, right here. Oh, it's got a metal and a non-metal right here. That means it's an ionic compound, and if it dissolves, it's going to be a strong electrolyte. Okay, chlorides. Oh yeah, chlorides right here I just learned about. They can be soluble as long as it's not silver, mercury, or lead. Oh yeah, so it is soluble, and therefore it is a strong electrolyte. So I want to illustrate these or write this one as Ca plus 2 and 2Cl minus. And I could put a little AQ down below each one of these because they completely dissociate in dissolved water. That's how you illustrate a strong electrolyte. HNO3, is this a strong, a weak, or a non? Well, let's see, it starts with an H and it's got nonmetals, so it's an acid. Is it one of the special acids? Oh no. Oh yeah, oh no, it's a strong acid. Since it's a strong electrolyte, once again, I want to completely dissociate or ionize it, and so I'll write it as H plus and as NO3 minus. Break it up completely, it will be those two ions. I can put a plus sign between these two, illustrating that those broke up and formed those two ions if I want much more of that to come next video cast. C2H5OH. CHOH. It's got an OH in it. Well, also notice that carbon and hydrogen and oxygen and hydrogen are both all nonmetals. Okay, so that means it's a molecular, aka covalent substance, only nonmetals. Oh yeah, there it is. There's an example one just like this. This is called ethanol, and it is a non-electrolyte. And so when we write this in an equation, or when we illustrate it, we write C2H5OH, and we don't split it up at all. HCOOH. Okay. This one's got H, C, O, and O. It starts with an H. Ooh, it starts with an H. It's got H. Does it have all nonmetals? C, O, and H. Yes. C, O, O, and H. Yes, all nonmetals. Therefore, since it has an H and all nonmetals, it's an acid. Is it one of the strong acids? No. That means this would be a weak electrolyte. And a weak electrolyte we just write as the formula. We don't break it up or dissociate it or split it up. Last one, KOH. Well, this has got K in it, so it's got a metal, and maybe that's the first question you should always ask yourself is, does it have a metal? And since it's got a K in it, it's probably going to be either an ionic compound or one of these special things. Oh, it has an OH. That's right, it's got an OH, and it happens to be a group 1 OH container right there, which means it's going to be a strong base. So this strong electrolyte would have to be broken up into its ions as K plus and OH minus. Now, if you're not sure of the little charges up here, remember you can always look on the periodic table, and you can look at the charges +1, +2, +3, and they're usually right. Or for polyatomic ions, you can look on the back right here, and you can find out what those charges are as well, if you forgot. So in the next video, we're going to take a look at different reactions types, and we'll specialize at one where solids form. And many times they form from different ions that are in solution, and so our ability to illustrate these will be very, very important. So we'll have to identify strong, weak, and non-electrolytes. Hopefully you learned that during this video cast. Next cast, you'll learn about what are called double replacement, aka metathesis reactions. And hopefully you learned how to illustrate ions. In this next cast, you'll learn how to illustrate solids in solution.